So Euler's method. It's a numerical approach to approximate a particular solution for a differential equation that passes through a point. So consider the following graph. If we have a picture like this, and I'll kind of draw almost the same thing again to help you understand it. So I'm going to explain this twice. But we're given a data point on the graph. So this is the exact solution curve, okay? Our exact solution would be on this graph. So you can see that that graph is concave up, right? And if that graph is concave up, it might help you with a question in the homework where it talks about whether this answer is an underestimate or an overestimate. But what we do is we take this point and we come up with this tangent line, which we know how to do, right? You know how to come up with a tangent line given a point. We take the derivative and we can find what the slope is, and we follow that for however long it tells us to. So sometimes they'll say that we're doing steps of 0.5 or steps of 1 for our x's, but we follow it for as long as the problem tells us to, and then we come up with a new approximation here. Okay, so we pretend that that is a point on the curve, and then we come up with a tangent line using that point and our slope given our equation here. And this would be what that tangent line would look like. And we follow it for as long as the problem tells us to. And we get our next approximation. And we could continue doing this. The next one would have a slope like this. So the next one would go like this. And our next approximation would probably be like here. Okay, so if the question is asking if this is an underestimate or an overestimate, is this an underestimate or an overestimate? It's an underestimate, right? It's underneath the graph and the actual value is up here, okay? Now this seems like a really complex and crazy process. It's not super complex because we have this wonderful formula here. Now, did I give you guys the packet of like crazy amounts of formulas? I think I did. That's like a packet I usually give like right before the AP test, but I figured it's kind of nice to have right now. If you look back in that packet, the front stuff, a lot of that stuff you're going to look at and you're going to go, okay, yeah, I know this stuff. It's just all the stuff that's on your AP test, okay? Like it includes everything from AB, everything from BC. But if you go way back in that packet, there's Euler's method. And Euler's method, you probably won't remember when it's time for the AP test, but this exact formula is in there, okay? So you'll be able to find it there as well. But what this is really saying is if we're trying to find the new y value, this is our next y value, our y sub n plus 1. So this is our new y. And I would probably write this on your paper. What you do is you take the old y value, the y before it, and then we add the slope at the old point times the step size, and the step size is always going to be given to you in the problem. And this here, I mean, you're going to kind of get used to using this, but this, if you write this across the top, it kind of helps you remember what all those pieces actually mean, okay? So I think what I have down below is pretty much the exact same thing here. So let's go ahead and actually try a problem. So I just put the formula over on this page so that we're not having to like reference back to it. Just a second. Okay. So here we're considering this differential equation. So they're giving us this, which is going to give us what that slope is, right? You don't need the sound, I promise. Okay. So we have this differential equation, and it's a particular solution. This is our initial condition. Sometimes when you see that stuff, do you guys remember that's like a separation of variables? Did that pop into anybody's head? Probably not this early in the morning. Okay, but when I see that, I go, okay, this is definitely a separation of variables problem. The thing with this is when it's Euler's method, they literally say Euler's method in the problem every single time. So it's not like you're going to go, okay, what am I supposed to do here? You're using Euler's method, but they're not going to give you this formula. So that formula is going to be something that you'll need to like have memorized when it comes to test time for this class and also when it comes to AP test time, okay? So we're starting at x equals 0. We're doing 2 steps of equal size, and we're trying to get to f of 1. So when we think about this equation here, I always just kind of lay it out with bullet points. I'm starting at x equals 0. And if our x equals 0, we can find the y value. Usually it's given right in the problem. So start at x equals 0, so our y is equal to 2. And then we can find what our dy dx is at that spot. So if I find dy dx at x equals 0, y equals 2, we're just plugging into this equation, right? So if x equals 0, this goes away, y equals 2, we just get 2. And then we're going to plug into here, and we have to think about what that step size is. So the step size, it's not like they tell you, okay, the step size is this, but they kind of do. We're doing 2 steps. We're starting at 0. We're getting to 1. So if we're doing 2 steps, aren't the step size 0.5? So it's always like given in the problem, but you have to find it. And usually on the AP test, it's like 2 steps. Every once in a while, it's 3 steps. But it's not like you have to do like 10 steps to get there, okay? So let's go ahead and write our y new is kind of how I write this. You can put your y sub n plus 1 if you want to, equals, this is the old y value, so 2, plus, this is my slope at that point, which would be 2, times the step size, which we said was 0.5. Does anyone have questions on anything I plugged in there?
Where'd you get the second 2?
The second 2 is this one right here, because that's this part right here is what our slope is, which is our dy dx. Any questions on that? Okay, so then this equals 3, right? So just for our notes, so that if we're looking back and trying to figure this out later on, this is after 1 step. And our data point would be 0.5 for the x, right? Because we started at 0, now we're at 0.5, we did that step, and now our y is 3. Is that making sense, what we're doing? So that would be our next, like, spot. Okay, so now I'm going to go down here, and I'm going to move to our next one. So our x equals 0.5, and our y equals 3. And we're going to find dy dx. X equals 0.5, y equals 3. I'm just trying to work on getting you guys to write things so the AP reader can see everything super clear. Okay, so if we write dy dx with this point down here, they know what we're plugging in. And we're plugging that into here, so take a minute or take a few seconds to do that. So do we get 4? Is that what you guys got? Okay, and I got my work here. If you mess something up, it's easy to mess something up. Okay, so now we're finding our new y value by taking our old y value, 3, plus our slope here, which is 4, times our step size. And our step size isn't changing, right? We're always doing step sizes that are the same, so our step size will still be 0.5. So we end up with 5, which is actually, I think, the answer here. Use Euler's method with 2 to approximate f of 1. So this is our approximation for our f of 1, and we'll write something next to here. So this is after 2 steps. Our point is 1. for the x because we went another 0.5 and then 5 for the y. So this is our answer for the problem. Any questions on any of those parts there? It's not crazy, right? And really that formula, after you use it a few times, you're not really going to have to look at it probably, but right away it's kind of nice to have it sitting right there. Okay, I'm going to give you a maybe 1 or 2 minute head start here to see if you can wrap your brain around this problem, okay? Because it's a little bit different. I'm not going to do like a bunch of the same ones. And then we'll start in a minute or two. But go ahead, write down some thoughts or circle some things or just sit and wait for me to start, I suppose. This is not as typical on the AP test as the first one. The first one is like very traditional and typical of AP questions, but this stuff here is things that they could do to like alter it a little bit, to make it a little bit more challenging. So I'm going to go ahead and read it from start to finish. So it says, let k be a constant. Consider this differential equation where y equals f of x is a particular solution with this initial condition. So this is my initial point here. Using Euler's method, starting at x equals 0 with 2 steps of equal size, we're getting to f of 1. So our change in x here, our step size should be 0.5, right? Let me know if I do something wrong. I don't like sitting and staring at my notes the whole time. And we know that f of 1 is approximately 17/4, and we're trying to solve for k this time. So did anybody actually solve this in that amount of time? It's fine if you didn't. And did you get, our answer should be -2. Is that what we got? Yeah? Okay, so how did you go about solving it? Either of you. Go ahead and unmute. I promise it works great. Okay, so go ahead, Meg.
Okay, so I started with the x and y coordinates, x equals 0, y equals 2. And then I found the derivative by plugging those points in.
Okay, so you did like what we did in the first problem, kind of like this, right? Okay. And I'm just slowing you down because everybody, some people don't have it, so they're going to need to write this stuff down. Okay, so if we do that, we end up with what for our slope? 2. You see how the x goes away? So that makes this problem way better. Okay, and then did you move over to the y new?
Yep.
Okay, keep going.
So I did y new equals 2 plus 2 times 0.5. And then that ends up giving you 3.
That seems good.
And then I kind of repeated those steps for the next one. So I did x equals 0.5, y equals 3. And then I did the derivative of that. And I kept k in the problem for this one because it doesn't go away. So it was 1/4 k plus 3.
Looks good so far.
So then I set up that same equation thing with 3 plus quantity 1/4 k plus 3 times 0.5. And that when I multiplied it out, got 1/8 k.
Oh, okay, so you combine like terms, I'm guessing, right? Yep.
Yeah. And then set that equation equal to 17/4.
So then we're really just solving like this equation here, right?
Mm-hmm.
Sounds good. Do you guys see where she went? Do we have any questions up to this point before solving? Is there anything you need to adjust in your problems? If there is, you can adjust it. That looks perfect, Meg. And then if we distribute this through, I'm assuming you did that. So we have 3 plus 3 halves, or we can just kind of leave it for right now. It's up to you how you do it. But then I'm assuming you subtracted the 3 and the 3 halves piece over, right? So do we get 1/8 k equals -1/4? That look good? And then finish by times them by 8, I'm assuming?
Yep.
Just got the right answer, so that looks good. Does anyone have questions on that process or need more time to write it down? Okay, so consider the differential equation. So we're given it again, k is a constant. Let y equals f of x be the particular solution to the differential equation given our initial condition. So I'm going to put my little boxes around this and this. And then Euler's method, starting at x equals 0 with 2 step sizes h, is used to approximate f of b as indicated in the table above. Solve for h and k. Do you guys like the challenge of trying it yourself first? It's probably more fun than just listening. Okay, go ahead and take a couple minutes. There we go, Claire.
Okay, so I started with x equals 0, y equals 1, like you can see there. And then your slope would just be -1. To solve for h, then, you know that the new y value is 0.5. So you'd have 0.5 equals 1.
And you know it's 0.5 because of this right here, right? This is our new y value after one step. Do you see that, guys? Okay, so when you do the y new, we're just going to put 0.5 in that spot. There we go. And then yeah, go ahead.
Yeah, then it'd just be 1 plus the -h.
Yep, because we put -1 for that slope times h was our step size. So does anyone have questions on this? Because this is how you solve for the h. Yeah, just hold up 1 second here, Claire. Okay, so if I'm, let me just write the equation right above here. Okay, so my equation is the y new equals like the y old or whatever you write there plus the slope times the step size, right? Change in x or step size, however you want to write that. So when we're looking at this here, this table gives us the step size because we're going from 0 to h. So that would be my first step, would be the step size would be h. And then my slope I know is -1 just by plugging in the 0 and 1 for the x and y. And the old y value we know is 1. And then the new y value would be this new value from the table. Do you guys see all of that? Hope, is that looking okay? I know you were like, this doesn't make sense. Okay, then once we get to this spot here, you can just solve, right? So that's what you did next, I'm assuming, Claire?
Yeah, so that would solve h for 0.5.
Okay, so then h equals 0.5.
And then you still have to find k, so you would start at x equals 0.5, y equals 0.5.
Okay, so just wait 1 second. So this h now we know is 0.5. So if I replace this with a 0.5 here, this is my new data point, right? So that's where the 0.5 for the x is coming in, and then my y is 0.5 to go with it. Good.
And then you do slope for that as well, but the k won't go away. So you'll end up with 0.5k or k over 2 minus 1.
So that's just plug in 0.5 in for the x and 0.5 in for the y.
And then it says that, so your b equals 3, so your y new would be 3.
Okay, and it says b, oh, okay, b equals 3. I see what you're saying. So the new point would be this one here, right? So this is your y new. Good.
So that would be equal to your 0.5 plus k over 2 minus 1. times 0.5 because the step size is h. And then I just subtracted the 1/2 over. And then divided by 0.5 and solved.
Okay, so then it's just a matter of solving this from here. Good. So you divided the 0.5 next. I like that approach. And you could distribute and all that too. It'll get you there, but this is kind of a more advanced approach, I think. So we get 5 equals that. Okay, so we're getting 6 equals 0.5k. You divide by 1/2, you get k equals 12. That looks good. Okay, so I'm going to leave that up there for a minute. See if you have questions. If you have questions, you can just direct them right towards Claire there, okay? She's an expert. Does anyone have questions on this? Okay, these are not as typical, okay? The homework problems that I'm giving you out of the book are going to be a lot more typical AP type ones. I just know that they like to try to do things like this in there. So I like the idea of trying a little bit harder problems when we're here together in class. Okay, then what we have for homework is this in your book. I still have to post the homework pages and the answer key, but I'll post those here in just a moment. And then there is this bonus problem here too. The bonus problem, it's just for you to try for homework, okay? We'll check the answer then on tomorrow, I suppose. We have class tomorrow, No, we don't have class tomorrow. What am I thinking? We have class on Friday. So we'll check this answer on Friday also. Just consider it like part of your homework. But these are a little bit easier problems. This one's a little bit harder, okay? So I want you to try the homework stuff from the book first, okay?